Hello, 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 hello. দিলে আছে। এখন শুরু হবে।
পয়েন্টটা নিয়ে গেছি।
পয়েন্টটা ওভারে আছে।
হ্যাঁ, বলুন।
হয়ে যাবে, কিছুক্ষণের মধ্যেই শেষ হয়ে যাবে।
আমি বাইরের দিকে আছি।
হ্যাঁ, এই যে ঢুকবে সবাই তখন চলে আসবে।
আচ্ছা ঠিক আছে, সব রেডি আছে।
আর সাউন্ডও দেখে নিন যে এখানে শুরু হবে, 4টে থেকে তো শুরু হওয়ার কথা।
হ্যালো 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 হ্যালো, এই কাপড়টা পেয়েছি। হ্যালো 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 হ্যালো। এগুলো কি জানো? এটা যেটা আলাদা আওয়াজ হচ্ছে। হ্যালো হ্যালো। এই ওইটা না থাকার পরে সাউন্ড ফেটে যাচ্ছে।
ছিল তো, তখনও তো লাস্টে টপগুলো তখন তো ছিল, যে মাটিতে পড়ে গেছে। জ্যাকেটের সাথেই তো লেগে চলে গেছে। এখন ডিরেক্টর ম্যাডাম থাকলে যদি সাউন্ড কেটে কেটে যায় তখন আবার উনি ইয়ে করবেন।
হ্যাঁ, সেটা জোয়ার করবো করছে এখন। এই এডিসি থেকে আনতে হবে।
এবার যদি টাইম আছে যদি।
আমি চাবিগুলো নিয়ে আসছি, তো না হলে ভালো না।
হ্যাঁ স্যার বলুন। স্যার হার্ডওয়্যারে আছে, এখানে বলুন স্যার। হ্যাঁ হ্যাঁ হ্যাঁ, ওই কিছু জিনিস লাগবে বলছিল। আমি বললাম মেল করে দিতে আমাকে, তাহলে আমি মানে মেল করে দেবো। হ্যাঁ হ্যাঁ হ্যাঁ। আচ্ছা আচ্ছা তাহলে আমি একবার আব্দুলের সাথে কথা বলে মেশিনগুলো একবার চেক করে নিতাম, তারপর আমি তাহলে দেখে নিই একবার, ঠিক আছে? হ্যাঁ
So I think
হ্যাঁ
you first take care of your.
হ্যাঁ 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 একবার দেখে নিচ্ছি স্যার, ঠিক আছে ঠিক আছে।
Correct, right? Sure.
না আমি তো স্টুডেন্টকে তো দেওয়া স্যার 10 বছরের
What's
পুরনো
the
হয়ে গেছে বলে
trans-
সেজন্য
did
ওদেরকে
you
দেওয়া
send
হচ্ছে,
the email
কারেন্টলি
to
যেটা এখন
talk
করা
to
হচ্ছে,
something?
চেঞ্জ করা হচ্ছে যেগুলো, ঠিক আছে? তো আমি
Automatically,
একবার
right?
দেখে
No,
নিই
I think
মেশিনগুলো
it
স্যার,
will.
আব্দুলের সাথে এ করে তারপরে আমি স্যারের সাথে কথা বলছি এই ব্যাপার নিয়ে,
Yeah, yeah, right.
ঠিক আছে? করে ওটা ফ্যাকাল্টিদের তো বোধহয় 5 বছরের পুরো শুনেছিলাম। হ্যাঁ তো ল্যাবের তো ঠিক আছে স্যার, আমি একবার তাহলে স্যারের সাথে দেখে নিই মেশিনগুলো, দেখে দেখে আমি স্যারের সাথে কথা বলছি। আজকে তো বোধহয় স্যার নেই, আমি দেখতে পাইনি স্যারকে। তো বোধহয় হ্যাঁ 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 হুম হুম হুম। আমি তাহলে স্যার আপনাকে পরে আমি জানাচ্ছি। হ্যাঁ 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 ওকে।
Should I put it there?
জয়েন টু দ্য গুগল মিট।
Oh,
হ্যাঁ
want me to join
হ্যাঁ
Google
হ্যাঁ
Meet?
ইয়েস স্যার।
Oh,
হুম
no, but you have to send the email. Huh?
জয়েন টু দ্য গুগল মিট।
Should you want me to join Google Meet?
ইয়েস স্যার, দেন ইউ ক্যান শেয়ার ইউর স্লাইড। হ্যাঁ স্যার ওকে ওকে স্যার। হ্যালো হ্যাঁ 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 ওকে স্যার ওকে স্যার হ্যাঁ 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 এই স্টার্ট হচ্ছে তো ওই জন্য স্যার এসে গেছেন, স্পিকার এসে গেছেন। হ্যাঁ
Yeah.
হ্যাঁ আমি স্যার আপনার কাছে যাচ্ছি তাহলে। হ্যাঁ 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 ওকে। I'll tell you the code sir.
কোডটা আপনি বলবেন?
হ্যাঁ কোথায় বলুন? meet.google.com এ search করবো। meet.google.com। I will connect, but if there's online participants, they cannot see your slide. That's one. I will connect our HTML cable so that y interpret y u x n z z y u x hyphen hyphen small
I have sent
y
you the thing.
small y u x y u s hyphen hyphen f z z t hyphen t n z z t w t d
Thank you.
hyphen w t d
Thank
f
you. Thank you.
hyphen w t d. If you put your speaker, microphone, and this one.
No.
No, after one. You can use it. You can use it.
No, wait a minute. If you share this.
You can do that also.
No?
Yes, sir. You can do that if you make the screen size bigger. If you use it, that's what I mean. Or else you can share your screen, no problem.
Let me see that I can share this. আমরা এখানে প্রজেক্ট করতে পারবো তো টপ that is better for us. Correct? Yeah, I don't know how to share it, but
Share your entire screen.
no, share.
Share. Can you share your slides with us?
No, this is moving in this. So can you give me the HTML?
Yes, yes. আমি তোমাকে জয়েন করতে পারছি, শেয়ার হবে না যখন, তাহলে আমি তাহলে এই স্ক্রিনটা কি ক্যামেরাতে দিচ্ছি, এখান থেকে yes. Mike is Mike is
No, that's disconnect me out.
no, you are sharing it from here.
Then I'm out.
Yes, you don't need because I will share it from here. Screen is not
That's what I
showing.
said in the first place. Fine.
Doesn't work now.
Okay. Changing slides.
You need a pointer, sir? You need pointer?
Yes. I can use a pointer or I can see. I can use a pointer.
Okay.
No, can't connect with this.
Oh, okay.
It's okay. You have a pointer, right?
Yes,
I don't need
we
slide
have a
changing.
pointer.
I'll do it.
Okay, okay, okay.
Okay.
Is it okay? Is it okay to record your talk, sir?
This is a USB.
You have a USB. Pointer you can connect.
No, it won't work. No, it doesn't work with iPad.
Oh, for the changing the slide, the pointer you can connect. But the changing slide doesn't work with this.
Okay, maybe take another 2 minutes, and in that time I will note down some of the things. So yeah, please. Yeah, you already have something. No, that's your academic thing. No, so this I have your sort of okay, but like time limits. Can you see? Teaching student. Yeah. And then postdocs were
এটা জাস্ট লাগিয়ে দিন না ওগুলো অত কিছু করার না এই কভারটা জাস্ট লাগিয়ে দিন
হবে
কভারটা কিছু করে লাগিয়ে দিন
ঠিক আছে আমি এগুলো রেখে আসছি
এটা একবার চেক করে নিন ফার্স্ট
and then you join directly.
ঠিক আছে স্পিকারটা লাগিয়ে দিন
It's actually let us wait for another couple of minutes. Sure. Good afternoon, everybody. It's a great pleasure to have Professor E. Sunil Kumar. So he's presently at the Department of Physics, Center for Soft and Biological Matter. Uh, so he's a chair professor there. Sunil is a reputed statistical physicist and well known in our soft and active matter community. So you know him, I think, I don't know about the students or faculty members, know him quite well. So just a brief introduction to his academic career. So he did his MSc from University of Calicut. I'm not mentioning the years. It's informal. Did his PhD from RRL and then a couple of postdocs at Institute of Mathematical Science, Chennai, and Max Planck at Bonn. He joined as a professor at IIT Madras in 1999. In between, he moved to IIT Palakkad as the director, and recently came back again to IIT Chennai at on in 2017. Sorry, he was the director since 2017 to 2022, and came back to IIT Chennai, where he's the professor. Today, he will talk about collective motion of self-propelled ring polymers on circularly patterned substrates. Sunil.
And all of you who giving me this to talk to you. And
Yeah,
so,
Sounded, yes.
can you hear me now?
Yeah.
Okay. So it's a great pleasure to be here after a long time. Okay. And so that's partly because I've been various administrative duties in the past almost a decade. I got back to working again full time. So it's very nice. So this is a work which I want to talk today about the work which I did with a long-term collaborator of technology, and actually a master's student. Um, it's about motion of self-propelled polymers on circularly patterned substrate. The motivation for this is twofold. One is, of course, it is as a model for self-propelled particle. There are a lot of done on self-propelled particles. So if we're looking at sharing motion and motion agents, clustering, things like that. And the second thing is also that it is trying to develop this as a model for sense, emotional sense. Not very far with it yet, okay, but I will tell you that. Okay, so if you look at the motion about this self-propelled particles, a variety of geometric shapes, interactions, and driving mechanisms, and stuff. And for to understand relativity, lots of things of this. Okay. And so, just give you a few examples. There are lots of work. It's a huge volume of work. Yes, I'll just go through all of it. But it's just very important that you can say this. So the first one is, of course, the famous celebration model, Richard. Okay, the Richard model actually takes as point particles, and it's actually a PhD work of Richard. Right. And this is where it takes a set of point particles, okay, and point particles move with a constant velocity. Then there. Okay. So the set of point particles all given constant speed. And random velocities, and then to begin with, and then there is an interaction between these particles. Secondly, they was aligned. Now they come close. There's a range of interaction in which they will align the mass. This is a very simple thing. Okay, and then they look at it as a function of density, and then you say as increased density, you see this clustering of these particles, and the particles move around. So the screen will be a little bigger, but I hope I will see it. And they cluster and then they move around. And if you increase the noise further, again kind of randomized. Okay, but then if you increase the velocities further, then they will actually. So if you increase the density further, this is low densities, okay, and you increase the density and the noise, and then can get randomized. But then at higher densities, they all align. The whole particle system align, okay, and then they all move in a direction. And this transition was shown by Richard. And then after that, this same model is now with still point particles, but point particles also having a kind of a dramatic field association. Was done by Saturday's group. Okay, so they have done a lot of Saturday's group, and they have done a lot of work on that. And then they look at both the velocity alignment and also an imaginary alignment. And they show that there's again clustering. And then there are other models. Now these are not point models. And then there are disks. 2 dimensions again. Okay. And now these disks, in the case of disks, again there is the disk can come and contact and come in contact. And now there is a this kind of disk forces that they exhibit what is they call the contact emission of the particles are moving, okay, and then they can come in, then they come in contact, okay, and they have a force acting on them, and then can reduce its velocities, and then this contact integrated flow motion. This is and there are also other models which looks at that. Now going from a disk to a rod, set of rods, okay, was again done by the Bernalian group. Okay, the same people did this work. Okay, and they have looked at the rods, and then they look at the clustering, motion of connected particles, etc. Both with pneumatic and an active force in a direction, and show that as you change from square to a long even particle, there's more cluster. And then there is this. This is the one of the latest ones. Okay, and these two, in which here they look at a set of 2 particles, okay, 2 disks, okay, on 2 spheres it could be, and they do 2 disks here, okay, and this is in which again there is a force which is proportional to the force on this in the direction of the big particle, from the small particle to the big particle, but that force is now proportional to the separation between these 2 particles. But again, when the 2 particles, the 2 of this opposite particle collide, and if they change this distance, and then they can slow down. That can again give you contact. So this is some set of models which is starting. Just look at not a completely random sample, but some I think is important to the work present from 1995. Okay. Now this is all in terms of self-propelled particles. Okay, so now in terms of cellular, basically for 2D typical cell modeling, people use and 2D and 3D you can use it. So both a set of network called reconnection models, they call it. Those are called vertex models. And phase field models. So these 2 models have modeling cells, okay, and as a polygon, and then you have contact, and then for the movement of this thing, you can switch the connect this connecting faces. You can switch them, and then you can change the shape. That is one set of work. Which looks at cells in 2D. Another set of work, the models, this is again a set of cells. You can think about a set of cells in 2D, and each of this is a field. So there are n particles, there are n fields. and each field is centered at some point. Okay? And then you have a handshake to start with for the field, okay, and then these fields boundaries can interact, and they can put in connection between these things in the model. It's come recently. So it's a very involved thing to look at space models for 2D sets. So there are mainly because you have to calculate the boundary of every set. So now one of the problem with all of this models is that this okay, all these models assume confluence to be close to 1. That your packing fraction is almost to 1. Because every cell should be in contact. If you want to define this cell here, it has to be in contact with another cell. So the confluence has to be almost 1, very close to 1. If you don't have an isolated cell or you have low densities, and then this kind of model.
What are the arrows?
Arrows are actually polar forces. And so there is also a polar force, and there is also a force coming from the boundary of the each cell is actually also having a propulsion ring. So this is the arrows, and then you can also have arrows coming from the longest axis. I think that is also shown in this side. That's like a dramatic thing. Okay. So, so this is what. So now what I wanted to show you here is that model this kind of self-propelled particles cells using a simple ring polymer model. It's a triple model, but it's a particle-based model. The advantage of particle-based model compared to phase field models is that it's easier to calculate. Okay, and and I say that can represent because I have not done that. I'm not going to talk about the cell thing here, but I'm going to talk about the ring model. And so you can then do a deformable cell with various cell densities. Let's see why I can say that. Okay, so so this is the model. Okay, so this is the model for the ring. Okay. So the I don't have so many things to say, so you can stop me on the way. So so what we do is we mark out the, let's say we mark out the boundary of the set. Start with it's a circular set. And then we represent that by a set of beads and spreads, simple enough. Okay, and then we mark 2 points as its polar sets are polarized here in this case. Then we say okay, these are the polar points L1 and L2, and there is a vector P which just connects this. Now we'll see what are the forces on the potential of this. This is the so you can actually apply polar force. Okay, now this is going to be cells are actually. So the way the cells move is like they have this Fourier and they put in those factors on substrate and apply a force on substrate. So of course we are not in this model. We will not be considering the substrate process. Okay? So substrate is taken to factor, and then we talk about the net force which is acting on the cell, and that is what this is. I say that because generally people will say active thing, they would think about net force being 0. Okay? And here there is a difference because this is on a substrate and things are moving, so there is a net force acting on particles that sense it's kind of also a driven system. Okay, so now this is the potential energy of the whole ring. Okay? The ring will have the bond energies, okay, and so the bond energies are given by this harmonic spring. So these springs are all harmonic. Okay? And then you have there's a repulsive force between if you have multiple of this polymer, so this ring polymer. There's a repulsive force between them, and the repulsive force is also taken up. How many people take it, etc. We use repulsive force as also harmonic, just to keep computation simple. And it's okay. So and then you have a bending force because this is a semi-flexible. So there's a bending force, okay, and that bending force is taken 1 minus cos theta I, where theta I is the angle between this and that. Okay? There's a free body force here. Okay, and that's theta I, and we'll take this theta I to be 180 for each of them. Sorry, yeah, sorry. Instead of 1, you could put a cos theta 0 minus cos theta I, and the cos theta I can 0 take like 180, theta 0, that's why it's 1. Okay, and so you can put it as 1 minus whatever, and then 1 scale. Okay, and then you can get the body force. That is the bending focus. I will come to that. We can also put a preferred angle instead of being straight. You can also put a preferred angle. So this potential will make it straight. Okay, but you could also put a preferred angle, and the preferred angle we do keep it to change the shape. So I'll come to that. Because this is a bending force. Okay, and then you have an area compression term here. Yeah. So there is an area compression term. Okay, here. Okay, so the area of the ring is kind of kept constant, or compressibility term. Yeah. Okay, and chi is a compressor. So the area of the ring is also constrained. The area of the ring is constrained. The bending is constrained. Okay, and there is a repulsion between the to prevent overlap. Okay, so if you just keep a free polymer here, it will give you a circular shape. And so that's what it is. Okay. Now that's a potential energy, and then there's a propulsion. Now this propulsion is spend a few minutes on that. So this is a propulsion force. They said this force, every thing is coming from the fact that the cells move. Okay, by exerting a force on the substrate and using the reaction force to move. Right? And this is a reaction force. Okay. And this force is taken as in the direction of this force. Okay. And it is then equally divided among all of them. Okay. That is what n is the number of seeds. Okay. And so that is yeah. Okay. So this is a number of beads in the polymer, and that's polar direction. Then there is a term here G. Okay. Now this G is actually plus or minus 1. Okay, and this is actually here the VL is the velocity of the particle. Okay, and the G is dotted with the velocity of the particle integrated over some time. Okay. And the average, because this is a bar here, is the average velocity integrated over time. So this is important here. So let me tell you what this is. Okay. So this is a unit vector here in the direction of propulsion. Remember, this is the magnitude of that force, okay? And the force is then divided among all the particles equally. And this d term take plus or minus 1, which means that let's say there is an isolated particle, okay, and it has a force given in a time equal to 0 in this direction, okay, and it will keep moving straight. Okay, it will keep moving straight. Okay, this particle, because the v and the p will dot be always be greater than. It will keep moving straight. Okay. And let's say it's a boundary or it's something else. Okay, there is a block. Okay, and then the v will go to 0, right? And then the noise will take over. Okay, and then this could change something. It could reverse direction. So basically, the time at which we integrate this tower will determine some kind of persistence time of the run of this resistance time. That's what you're doing. And it gets switched.
So L1 and L2 are then sort of defining the direction of movement, right?
It's fixed on the cell. Okay, so that is what it is. Okay. Now the preferred angle at the poles, as I said, the L1 and L2, we call it poles, can be changed. Okay, and the preferred area can be changed, and that will determine the shape of the cell. I could keep them at some place at 30 degrees or something like that. So 180 degrees, then it becomes a wrong cell. So I can change the shape, the preferred shape of the cell. If it's a preferred shape of the cell, because cells are still flexible. Okay, so that's what it is. Okay, now given all of that, we just use the usual molecule. T. Okay, and so there is an inertial term here. Okay, it is low new value, but still there is an inertial term. Okay, and then the usual forces. Okay, and that's what we have. And this is the active force, which is now they said it's from the test, and this is coming from the potential thing, so the force. Okay, and then there is a friction, and this is noise. That's what. So now, given that, okay, and now, so that's a model, okay, and you have the particle which can move with the force, can move, and it has flexibility, and you can have lots of this. You can see that using an elongated path. And now, this is, remember, this is actually, I cut and paste from paper, and it's always done in reverse direction. So this is force going this way, okay, so this way is decreasing. This is the lowest force. Equilibrium stuff. Okay. And what I showed below is the direction of the velocity. Okay. And so you can see that this density about 0.315, okay. And there is random motion of the particle. Okay. And as I increase the force, and all I'm doing here is keeping everything else the same, the polar angle there is a elongated cell, and I'm just increasing the force. As I increase the force, I see cluster. Right? That's obvious. Yeah. And you can see that as you increase the thing, you see clustering, and you can also see velocity. So you can see this. Okay. This arrow is very.
Which way the AP is directed leftward?
Which one here?
Direction of the force.
It's along the long axis of the.
Along the circle.
Yeah. Okay. Right. Actually, this arrow is not visible, but all the arrows are pointing this way. So this cluster is basically moving. I'll show movies in.
So how is it two rings? They interact with each other. Again, we have two rings.
They're only repulsive.
There's only repulsive.
This thing only repulsive.
Okay. Another in the last 40, the biggest force you have here, the whole cluster is moving leftward, as you were saying. Now I see the shape. There is also an asymmetry. Not only the particles are oriented this way, but the cluster is also thin along this direction and along this.
Yeah.
Is that a real effect, or this is just?
It is. It's a real effect. It is. Actually, there is now. There is a. We'll see that how the particle decompose. So there is a direction set by the forcing, right? The air. Then there is a direction which is the longest axis of the race. Then need not be the same.
So that is set by theta. Long axis.
No, so theta decides the L1 and L2 points, which is a polar axis. Okay, so that is the direction at which the force is moving. Okay, according to force, but then the cells can deform. Okay, because it is something else here. Yeah? It can deform, and when they deform, they need not be elongated along the direction of the polar. Okay? That's why you see that shape is not really. Okay, so now. So what I'm trying to say is, okay, now shape is important. Okay. Now in this case, what we're showing is that if I have circular, I show you elongated one. I'm showing the circular one. Okay, same forces. I don't see cluster, and you can see that the velocities are also random. There is no cluster in the circular. You have to let it elongate to form large cluster, and that's particularly visible in the velocity space than when you look at the rings. Okay, because the velocities are completely random, and that is can show you in the movie.
Okay,
Yeah.
ensure the circular thing, you make the
angle to be. So now you can see that these particles are moving. Okay, the clusters are very dynamic. Okay, and but then they cluster and they move, or things go opposite direction also. Sometimes they cluster break and rejoin. These are all the periodic boundary.
So there is always a finite particle current in it, or at some critical value. I mean, when they are say
There's always some low. Actually, very low at some density. It is very low. you start seeing this cluster, and there's a finite particle.
So it's moving upward, not leftward.
No, this is moving up.
What?
This is pretty good. You could take any random direction to move. Yeah. So it could also change as a function of time. But now, if you look at in the case of circular thing, you don't see that. Okay?
No, so that is my question. Long time average, I mean, there is current or not no current?
Oh, you're saying at any
large,
the average over thing, it should be zero.
So
Because these clusters are dynamic.
This is a persistent current sort of.
Right. So see, there is that's where the persistence time also comes in. There is a time at which you do get it. So yeah, so you can see that this is kind of random. Okay, the only difference between these two models is the case that the theta is 120 or 180 and circular.
You never find the long time non-zero motion because you have an external FD.
Yeah, but then FD is set along in each range, not in a. So that is yes, you see that. Okay. So then just showing that here, the same then proposed density. If you have elongated particle, you have very clear. This way and this is going that way. Okay. So that is thing. So the takeaway is that the clusters are dynamic and circular rings, conveying this. So now I can compute a few things here. Okay. I can compute what we call the mixture order parameter, which is basically the velocity, the speed, the velocity of correlation. Velocity correlation. Okay, you can compute that, and that we can actually show as a function of mg, the driving force, and you can show that this velocity alignment, okay, the velocity order parameter, actually shows a transition, something like a transition, okay, a continuous transition, at around a certain force 20, something. Okay, you can see that you can upload that. I can also calculate the second moment and the velocities, and then show that not only the average but also the second moment of the peak. So there is something happening around this point, okay, and you don't see that. And for elongated cells, even for a lower density, you'll see some change, but this is not as sharp. There is a particular density and a particular force at which you will see this transition, and then you have this. Yeah. So and you can also compute. Now this is for the velocities, and this is for the polar orientation. Now I'm trying to say that polar orientation is the L1, L2, I said the PL, okay, the direction of that. Okay, I can look at that or the order parameter of that. Okay, this is like a pneumatic order parameter, not in terms of shape, but in terms of polar vector. Okay, and then that shows also a change, but much weaker, and the peak is also much weaker. Okay, again showing that these two need not behave the same way. Even though qualitatively there is some similarity, but the number of the quantitative thing is very different. And now I can look at basically just to summarize, there are clustering, okay, and then there is velocities, okay, which can align, okay, and then there are polarities which need not be. So now, if you look at the cluster here, it looks like it is. If I look at the longest shape, if I look at the direction tensor and look at the eigenvalue, not the eigenvalue, there will be some alignment here, similar to this, but not in the middle. So again, showing that the shape elongation is not really coupled to that.
Pneumatic order refers to the polarity.
No, this one. So I could also compute this.
So you can also extract a length scale. So right, I mean, how far they are correlated in terms of polarity, velocity, and density. Yeah. Right. These three length scale,
they are not same. They are not computed. Yeah. Okay, so now just to tell you what the mechanism for this is. First thing is this mobility induced clustering, okay? And that is it's like this. Now two particles here. Okay, so they are what is shown as the black curve is the polar direction, okay? And and you can see that, and green is the velocity of the particle, okay, at that instant, and the two particles red and blue, and you can see that they are moving towards each other, okay, and then they collide, they of course change the shape, okay? And then you can see that the velocities change, but the polar directions are stuck there, okay? So they are pushing against each other. In fact, you can see that this is forming that cell. And so they continue to be in that direction, even though the velocities align. Velocities are aligned and they're moving now in the same direction, both the things, but these forces are still different. This is still pushing that cell, okay, in that direction. Okay, and then slowly the forces also align. When the forces align in the direction of the velocity, the cells separate. You take two of the cells that got this. Basically, the cells, because this cell is repulsion. Right? The addition is the clustering only because of this. And the cell is deep. And you can look at that in terms of the angle between the velocities, angle between the polar things, okay, and the number of monomers in contact between these two cells. And you can see that there's a time at which they come, collide, and they stay together, okay, and they separate. So that's why the cells are very dynamic. Yeah, these particles are very dynamic, as we saw. Yeah. The collision, addition, separation. Now, this basically the misaligned polarities keep the cells pushing against each other during the addition phase, and that's basically the mechanism. Deformability is important because circular cells can very easily reorient and then do it. So that's the reason why circular cells do it. Okay, so now that is for the substrate. Now we move to trying to make a small modification in the substrate. Now we take a substrate now which is there's a boundary. Basically, then periodic. Now, there have been many experiments in which they actually look at current points, cells and current point. Okay? So that's the motivation for us to do this. So we have a substrate here, which is now a circular boundary. The boundary is dark boundary. The cells hit that, they have a repulsion. Okay? And then you have an inner region, which is shown here as yellow, and where we have a tangential force. Think about this inner region being made of small grooves. These particles are confined. Okay. Right. So that groove has been shown here as a red line. There are over infinite number of grooves inside. Okay. So there is a tangential force. Okay, and that tangential force is given by this the potential. You put it as a potential, okay, which is sin squared phi L, where phi L is this angle with a tangent to that ring. At any point R, I can make a ring. Okay, and the tangent to that ring and the polar direction of that. Clear, right? So there is a trying to cell is the polarity is trying to align tangentially to every point, and that is what it is. Okay, and then there is a constant here Ks that called for substrate force. So that's the parameter which is going to control how strong this alignment. Yeah. So there have been some experiments in which people have looked at this, okay, and there's also a Japanese book which looks on that, and they have recently science paper just last year, right? So a few months back, and it's completely research that they don't understand, but they have completed the paper with this set of work. Okay, so now I don't get into that because there's a whole question of what is contract and extent side and all that stuff. So you're not getting into that. So we're working with sets, and here we're just looking at this particle. Okay, so now again the net potential is just changed in the thing that there is a substrate. So there is a substrate force coming out that on every again the force is divided among every beams. Okay, and otherwise it's all the same as before. Okay. So now I just show you this. Okay. So what I'm doing here, this is a case in which two cases in which substrate force is 0. Okay. The density is kept at 9. Okay. and now the density is kept everywhere the same. The first two, the substrate 0, and then I turn on the substrate force down here, and I keep the substrate force the same on this, but I change in this 3 the driving MP. Sorry, MP is also kept the same. Uh, uh, yeah, okay. So I kept this is 3 cases are same. Okay. So here the rho is the force drain and height, all of them are same density. Okay, and these 3 cases and substrate force and the driving force, everything is the same. And R here is the radius of the component. Okay, so now let's look at that. Okay, so this is what you see. Okay, now this is the case when substrate force is 0. Okay, and you can see at this densities things move randomly. Okay, they collide and then they change. The small clusters are formed. Some clustering you can see at the boundary, which is normal because it is the boundary. Okay, but there is no particular thing like this. And that's there. Okay. Now I increase the driving force a little bit here. Okay, and yeah, here also we increase the driving force. The driving force increases by 20 to 22. Okay, and when we increase the driving force, you can see that again substrate force is of 0. No patterning in the substrate, only the boundary is there, and you can see as it's hit the boundary, and then they say that it starts moving in a particular direction. And this is very common. Okay, you see in all experiments. Whenever you have this, even dry systems like the vibrating wave particles also show the same thing. If you have a boundary, it's a boundary and it can get a circular turn.
And the sensor motion is
We're done. Okay. Once it sets it, it can change. But
okay. That's why I find it.
Yeah, but it can. It's a random thing. There's no particular thing.
But inside the part,
In this case, it is move randomly. So there is no particular. But also see that we use substrate. If you have a substrate force, okay, and this is the case where you can now again go back to this force, okay, low force, okay, and you can see that now there's a pattern coming here. You remember this whole thing was pattern, but there's a depletion here of particles. Particles get depleted from the center. It goes to the boundary of that pattern, okay, and sets up a motion. You still don't see too many accumulation at the boundary because it's the same density of that, okay, and same forces in that. Okay, you don't see too many accumulation at the boundary, but this boundary has a lot of power, and it sets up that motion in the particular direction. And again, there is no reason why it should be clockwise or anti-clockwise. It can happen, but once it sets up, it will come. So now, if I increase this force a little bit, okay, and that's what you're seeing there, and now particles go to the boundary, okay, and then there is a boundary motion here, okay, and there's a inner. So if you have more forces acting on the particle, they can escape from this region of pattern thing, and it can go outside, and then can get stuck. But there is a ring here still, and there's a depletion. And you can see that they hit, then they can align or they can change things. Now, this is a case where they're both moving in the same direction. Okay, but this is, as I said, it's not very set. They can also be moving in opposite. There's no real coupling between these two. It's an density. And these densities and these forces, there's no real coupling. Okay, they can actually set up in a pattern. So there's a straight force here, and there's a there, and the both creates this vertical motion. So that is what we have in this. Okay. So now this is just summarizing the same thing. Okay, showing that there's a pattern here, and then you can as you increase the force here. Okay, there are more and more particles get out of this ring pattern region, and more things go to the bottom. As you increase the force, you can see. And as you increase the force, if there is no patterning also, then there will be more things to go to the bottom. And you can quantify that. You can actually calculate the density in a particular ring and a particular thing. Okay, and you can write a road as a function of radius, and then you can show that there is always a peak. And this is a case where there is no pattern. Okay, when there is no pattern, there is nothing happens at this point. Okay, at the moment there is a pattern, there is a peak. Okay, and the force and the number of the density here is higher for lower forces. As you go higher and higher, it comes down, and more particles. So, so now you can also compute a quantity, let's say C here, okay, which is basically I can take any particle and look at whether it's going clockwise or anti-clockwise. Let's say it's clockwise +1, anti-clockwise -1, and sum over all particles, take the average, okay. So take sum over all particles, okay, and then take the average of that. Sum over all particles of the propensity direction, and then you average that, and that's not problem. See here, something to quantify whether it's going clockwise, and I can plot that as a function of the driving force. And you can see that here. Okay, this is a case where substrate is 0, okay, and then the very high forces, as the force of the thing, it goes from 0 to some non-zero value. Okay, again, this is a mod I have taken. Okay, so ±1 count here. Okay, so it goes into the high value because of the boundary. It's hitting the boundary. So basically, this red is representing this case, where you have things going in the boundary and deciding which direction. But if you have a substrate force, okay, you have a substrate force, you can get either, as I said, opposite vortices or the same vortices, depending upon that, you will get either going up like that, or there is a region here. There is a region of force, okay, at which you can get the inner and outer vortices moving in opposite directions. Okay, so you can get it. That will be a dip. Because you can, and then you get it. Okay. And now in this region, this pink region here, if you increase the substrate force, and there is an increase in the value.
So, was a physical reason that the particles are moved towards the boundaries? I have to understand that.
Yes. So there is a. I will show you. I'll show you. This I think is actually a question. Okay. And you can see that a single particle, if you look at, okay, and this is straight, okay, and you can see that they are kind of spiral out. Because there is some inertia of the system, right? And there is particles are moving, there's a force, right? It can move and move, but there is a substrate force is trying to align it, so it kind of goes in a spiral pattern and it gets out of that. And that is what I show here. Okay, finally spirals out and goes and hits the boundary. Yeah, it can also change direction and come back inside later. So there is a flux inside. And so there are things coming in randomly. There are things going out at the same time. And they kind of have to have a balance in this boundary. And that is what is leading to that. If you look at this is the perpendicular force, radial force, okay, and velocity, okay, of the particle, and you can see that things are going spiraling out, okay, and then they reduce the thing, and then again they spiral out. So this is the region where they accumulate, okay, and you have to velocities happen. Radial velocities are lowest at this point at the boundary between these two, and that's what that is. Yeah. So basically, that's the reason that there is an aligning force and there is a driving force, and they're both competing, not competing, but they're both acting at the same time, so they get this spiral.
It should happen for other geometry also, right? I mean, basically, it's a competition that decide to.
Right. Other geometry,
Like, I mean, if you take a square or
the boundary, yeah, boundary, because as long as there's a
there's a
boundary,
limiting boundary, and there's a
as long as the boundary, but the inner one will anyway happen because of the patterning. The outer thing will happen. As long as your topology of the ring,
then it's simple. Yeah.
Okay. Now I want just for a conclude, I want to show you the effect of the packing fraction. Interesting thing. So now, so far I showed you low packing fraction. I'm going to show you higher packing fraction. You're already about 0.4 maximum. You're going to 0.6. Okay, and you can see that again the ring is there, okay, inside, and you can see that there's a pattern inside, so there's a depletion zone, and things are moved out, and they're all moving in direction, and you can see that. It's also some exchange for particles in the boundary and inside. Now, if you go to even higher packing fraction, okay, about 0.836, then something interesting happens. There are things moving in one direction, okay, and then they suddenly change the direction. And then they keep doing this. So you can see that the change happens in the center, okay? And then it can propagates out, and then it we don't really understand this, but you can see that only thing which we could certainly say that this starts in the center, right? And then they move on. Sometimes it fails, okay, and then it goes back, okay. But sometimes they win, and we can see that it's reversed. So this keeps happening.
KAC the substrate related thing.
Substrate.
So if KAC is 0,
yeah,
then also you see the circular motion.
You don't see this reversal.
But the circular
motion is there coming from the boundary.
Right. That you still see.
Yeah, you will see the circular motion, and then you will see the inner boundary somewhat dissolved. There is no real circle. But this is because of the substrate. Okay. So I can quantify that again. We'll be looking at this, the tangential velocity, okay, as a function of time, and you can see that it undergoes. Okay, if it's a no pattern, no pattern. Okay, then they can remain the same. Once a particular direction is set up, it will just remain the same. And while if you have substrate force, and then if you look at substrate force is 40, then you can see that it switches here and then can be there. And you switch back again. Right? But as you increase the substrate force, this frequency becomes. So you can have the frequency of that as a function of the density. If you show that, you can see that the frequency of the switching is 0 beyond 0.8. Above that, it kind of increases. Above 0.9, but this is what we can see that the frequency can increase. And we can look at an autocorrelation of this velocities. If you just see this in periodicity, what we see that there is some kind of quasi-periodicity, but it's not very periodic.
About the interval distribution?
No. Yeah, we have to look at it more. Yeah, so so that's what I said. We have not completely understood this stuff, and there are more things to look at. What is responsible for this thing? The only thing which I can immediately see is that it looks like the particles in the center when particles circulate and then they go back to the center and they have to get into the groove. They could get in two different directions, and if one of them gets in, they can. And if there's already, let's say, everything moving clockwise, and one particle tries to get in and anti-clockwise, it's forced to move into the other direction because of the force switching which we have. But if there are 2 or 3 particles getting into a small ring there, in the opposite direction, force. Yeah, so there are a lot of other statistical parameters to look at. What is the frequency of this? What is the interval? And what is the switching pattern? They're not done any of that. Okay, we look at again the auto parameters they set the function of phi. Okay, and then you can see that because switching, okay, this auto parameter kind of drops beyond 0.8. Okay, 0.8 is where this one. Yeah, so that's all I wanted to say about this thing, and that's the conclusion. And what we are trying to now do is first put high density, and then have cell-cell interaction forces, and then look at the ability. Thank you.
So thanks for the nice talk. So questions, more questions.
So what do you expect if you take, let's say, 2 different type of theta P, 180 and 120 mixed? So should it make phase separation?
Yeah, I don't. Yeah, it should.
I think it should.
It might, right? It might depend on how rigid it is, and it might make phase separation. You are trying to look at 2 different driving. The thing we do not see.
But shape should make phase separation. And then in the actual things, you should have some contact forces, right? Substrate.
Yeah. So when you do cells, then you have to have the boundary of the 2 cells of this things should have contact force, There's be sticking because there are this integrated proteins which actually sticking.
But that's going to modify Kas in the model.
No, Ks is substrate. Ks is saying that substrate there is a lining in the body.
Okay.
But there could be also
So returning force.
interbody interaction, which is also stored out there. Okay, and also, yeah, there can give rise to a force. In the real cells, there are these two cells in contact, and when they're in contact, that induces a rearrangement of the cytoskeleton in the cell, which will push it.
Yeah, but that's too detailed, right?
Yeah. No, that is what's been put in various models. Various models already have. Yeah. Just that we can do this more easily. And we're working on that, and also working on the 3D of that, which is triangulated surfaces.
Is it possible to say the direction of motion and the cluster formation here of different origin? Like the direction comes from the boundary conditions and clustering and other scales of motion.
You're right.
So those comes from the forces.
You're saying that the vertical motion, the vortex which is forming, is coming from the boundary or the substrate. That is the origin of that. And the clustering comes from the driving
Exactly.
and the deformability.
So in this context, I mean, how do you define the boundary? I mean, it's a WCA kind of repulsive thing.
Yeah, it's
or
a repulsive.
sharp boundary. It's not a harmonic thing. Or
No. Yeah. Oh, you're saying the boundary of the.
Yeah, boundary.
No, we put in a harmonic.
It's a harmonic.
Yeah.
But why it is so sharp then?
This we have to put in a little high K value, and it is being able to keep. Even the cell-cell interaction is also harmonic. It seems to keep it.
But you said the boundary of the substrate is hard one. Reflecting hard one, right? That's
No, it's not. No, it's only a repulsive.
just a harmonic interaction.
No question from that. Okay, if there are no more questions, so let us thank the speaker again.
Yeah.
And there is tea, coffee outside. Boundary is quite well defined, sharp cluster, but it is quite well.